Action.
So physics 7-1, here we go. 1 and 2 is mass and velocity. You could do those in any order you want to do those. 2 is vector. 3 is vector. 4, we've got two choices. They said unbalanced force. If you just said force, I'd go with that for a day. They also said impulse. If you like that one, you could go for that. If you wanted to hit both of those up, there's a bonus point for you. 5 is force and time. 1 point for force, 1 point for time. Question about scoring that up. So informational stuff. Our book never does an equation for momentum. They never do a variable for momentum. It's sort of strange to me. In the world of my college life, the equation I had was P for momentum equaled mass times velocity. But I'm never going to ask you for that equation. But if you insist on one, that would be the one that I would have to give you. Units for momentum. Did anybody pick up on what the unit would be? There you have it. It is either Newton seconds or kilogram times meter per seconds. I'm going to use Newton seconds. The book is more going to use Newton seconds, but kilogram times meter per second is just as good. The thing being vector quantities, what that means is triangles and programs could come up in this chapter. It's not going to be an everyday occurrence. It's not going to be an every problem occurrence, certainly. But every once in a while, you might see something hitting something from the side. And then vectors can come into play, and we might be doing some Pythagorean theorems, and laws of sines, and law of cosines. All that stuff can come in anytime there's vectors. Let me see if that's a question on the next quiz in a second. I'll just say it. It might make a chapter review or something. Momentum tends to change when velocity changes, because if momentum is mass times velocity, mass really doesn't change. So if momentum's going to change, it really can't be because mass changed unless you have like a melting ice cube or something. But the velocity is going to be what's going to usually change to change the momentum of an object. Unbalanced forces cause momentum. I have no comment on that. Here's an equation that you will use. Is Ft equals m delta v. What's the delta mean? Change it. Technically, this part is called the impulse. And technically, this is the change in momentum. But realistically, since they're equal to each other, they're like interchangeable. But technically, this is called the impulse. But in the homework, if they ask you to find the impulse, but you have the information to find this better, then do this. It's the same number. If they ask you to find the change in momentum, but you have more of the information to do this half of the equation, then just do the other half of the equation. It doesn't really matter. But Ft equals m delta v is going to run your homework tonight. Impulses produce change in momentum. We already talked about that. I'll do some math examples in a second. Here's something that I jotted down in mine, and maybe jot down in yours, because who knows, chapter review or whatever. Moving objects might or might not have an applied force. Moving objects might or might not have a force. May or may not. They definitely have momentum. Yeah, it's not a question, it's just a fact. Moving objects may or they may not have a force applied. We don't know. So moving objects may or may not have forces acting on them. They definitely have a momentum. Anything moving has momentum. How can you have a moving thing that doesn't have a force applied? What's that? Wow. If it's a constant velocity. Because an object in motion stays in motion. So something that's in motion stays in motion without any more forces. It'll just go. So moving objects, you might have a force there, you might not have a force there. Just because it's moving doesn't mean anything. Accelerating things absolutely have forces. That's one of Newton's laws, F equals ma. Forces cause accelerations. But motion, it might just be in motion because it wants to stay in motion. Side conversation, how could you have a giant truck with a low momentum? Go real slow. How could you have a tiny bullet with a really big momentum? Go real fast. It's not about how big you are. It's not about how fast you are either. It's about like a balance of the two. Bullets might not have a big momentum because they are small, and maybe they aren't going fast enough to really offset the smallness. An elephant might not have much momentum, but an elephant at full bore, I bet, has some pretty serious momentum. It's about a balance of how big it is versus how fast it's going. That's what momentum is about. Question about the concepts? So let me look at next quiz, and then I'll do the mathy stuff in just a sec. So what you're reading for next time, it'll have a 14-point quiz. So it'll be reading 7.2 and reading 7.3. There's going to be Newton's third law in there, and there's going to be another law in there. There's an equation for sure, there's a little bit of other information, but total of 7 points from another Newton law and another non-Newton law, and some mixed things. Compared to today's, after the 7 new ones pop in there, 1 and 2 stays the same, but I made it a 1-point question, so half point per blank. 3 stayed the same. Here's a new thing that I did say. Momentum changes when blank changes. Velocity, because we really can't change the mass. Blank causes a change in momentum. That's going to be one of the answers, because another question is going to be, what does an impulse produce? So if you're going to tell me that an impulse produces a change in momentum, you can't really use impulse to fill in the blank for what causes a change in momentum. So what would we have to use for that other one about what causes a change in momentum? Unbalanced force. And I'd be pickier there to want unbalanced force and not just force. Let's see. 5 and 6, that stays the same, but became a 1-point question. Half point per blank. And I will ask you for the equation that I put on the board here. The equation that relates impulse and change in momentum is Ft equals m delta v. You don't need the squiggly brackets in the words. Just have Ft equals m delta v, and I'd be a happy man with that. Question about change arounds? Yeah.
So the 2 laws are worth 7 points.
Yeah, there'll be a Newton's law. There'll be a couple questions about that. Then there's going to be this other law. There'll be a couple questions about that. One of those laws has an equation. That'll be in there. You put that all together, there's going to end up being like 7 total points. Question there. Homework, we're working 1 through 7, which will be like what's behind me that I'm about to do. So if I tell you a story and I'm talking about 40 newtons, that's an example of a force. If I tell you 5 kilograms, that is a mass. They tell you 9 seconds, that is a time. So if we go to stick those numbers in, we have force, we have time, we have mass. I could ask you one of 3 questions. I could either ask you for the change in velocity, I could ask you for the impulse, or I could ask you for the change in momentum. What would be the easiest of those things for you to do right now, math-wise, for what I've got? The impulse would be the easiest thing to do. Take F times T. F times T, the impulse is 360. And the unit for that was Newton seconds. Now that we have the impulse, it's really easy for us to do the change in momentum, because that's 360 Newton seconds, because these two things are the same. Did I have to do this one first to get that one? Not really, not if you just know that they're the same, just get either side and you double answers all the time. To do the change in velocity, we've got to do a little bit of algebra opposite time, take the 360 that we worked out and divide it by 5, and that's 72 meters per second. Question about that? If it were a test and I wanted the 3 sig figs, I'd have to go 4, 0.0. Question about stuff to that side of the line? So if I tell you another story, kilograms is again mass. If I tell you 2 rest, that means a final velocity 0. If I started you at 8 meters per second, that's original velocity at 8. 4 seconds is definitely a time. These facts on their own aren't useful other than they tell you the change in velocity. If it was 8 and now it's at rest, the change in velocity is 8. So if we try to work this equation again, we're better equipped this time to do the left side or right side? The right side. It doesn't really matter. I could ask you for the impulse. I could ask you for the change in momentum again. Or I could ask you for the missing item, which is the force. You'd have to get these first before we could get that one. What are these?
8,000.
It is 8,000. Agreed. Because we know the mass, 1,000. We know the change in velocity, 8. So 1,000 times 8 is 8,000. And then both parts of that equation are 8,000. To get the force, a little bit of algebra opposite, work off the 8,000. Just divide by 4, it'd be 2,000. Unit on that? Newtons. And all of these, if I wanted the 3 sig figs.
It's the third 0. I mean the second 0.
Yeah, that middle 0 just bar goes up. That's what the 1 to 7 should do mostly. But who knows? Because there is velocity in these, I wouldn't rule out you using any of the old velocity equations this chapter if the book decides to do a little review moment. I wouldn't rule out, since there's forces in this, what's our big equation with force in it? F equals ma. I would not at all be surprised to see some F equals ma activity somewhere in this chapter. Whether that appears tonight or not, I haven't looked. We'll find out together tonight into tomorrow at some point. But again, one more time, 1 to 7 is the homework. Read is 7273. 7 new points off of the read, 14 total points from putting the quiz together. Question about any of that? Okay, so let's hit a cut.
Cut.